Ehcache 2.0 was released last week on March the 9th, together with Terracotta 3.2.1, the latest version of our platform software. Ehcache 2.0 represents a really significant step forward for Ehcache, which is why we picked the 2.0 version rather than making it 1.8 or whatever. It really has two big investment areas. One is a large series of enterprise-class features, JTA being probably the most significant, and certainly for the focus of this presentation, the most significant. But there are also a lot of other features which will be very useful in enterprise-class applications, such as asynchronous write-behind to the database, optimized bulk loading, dynamic configuration of cache elements, as well as providing those enterprise-class features. And by the way, when I say enterprise-class, that doesn't mean that they're only in our commercial offering. They're in our open source offering. They're just enterprise-class. The other area of where we made a very large investment is in ease of use. So making Ehcache and Terracotta 3.1 extremely easy to integrate into your applications to scale them out. We provided full backward compatibility with earlier Ehcache versions. So taking an existing application which uses Ehcache, it's as simple as upgrading the jars, and if you want to use any of the new features, including the new XML elements in your config, to leverage those features. So really simple, ease of use, focused on enterprise class. So now I'd like to move on and talk a little bit about our JTA support. So with this release, we've added JTA support to Ehcache 2.0 with the Terracotta distributed cache. JTA, as I'm sure you all know, is the Java Transaction API, which is defined by JSR 907 and is one of the key JE APIs for distributed transactions across multiple JTA, multiple XA resources. So what exactly have we implemented in Ehcache 2.0 to support JTA? Basically, we have implemented Ehcache as an XA resource. This is a feature that you can turn on. So not every cache needs to be JTA enabled or an XA resource, but if you choose to make it that, then that capability is embedded in the cache. It's designed to work with any JTA compliant XA transaction manager, and we've tested with a broad range of transaction managers. And in fact, it detects the transaction managers out of the box. So if you're using JNDI, you can wire in your transaction manager of choice. The support is designed to work with Spring, with EJB, with manual transaction definitions or programming to the JTA API. So it's really designed to be very easy to integrate. So you'll integrate your transactional cache pretty much in the same way you would integrate any other transactional resource. One thing to note is it requires the Terracotta server, so actually the server-backed distributed cache, to ensure that the transactions are managed in a JTA, XA compliant manner. A couple of ideas about how people might use a JTA cache. When would a JTA cache be useful to you? One good example is when you have two caches and you'd like to do an operation on both of those caches or neither of them. So to isolate that set of operations in a single transaction. So you could imagine that one cache represents something that your inventory, and another cache represents the cache of items that are queued for delivery. You don't want to take something out of inventory and send it somewhere unless you actually get it into the queue to send it out. So you would want to group those two as an isolated transaction. And with the JTA compliant cache, you can easily do that. Another good example is where you would want to group transactional cache operations with other XA resources. So, for example, a database. You may want to update the database and update the cache at the same time so that you have a consistent system of record mirrored in your cache. And if the update to the database fails, you don't want to update the cache, or vice versa. Another might be if you introduce a JMS queue, a JMS XA resource. So you might read something off of the queue, and based on that inbound message, you might update a cache, update a database, or multiple databases, or multiple caches, and group that all as one isolated transaction. So using Ehcache as a JTA compliant cache lets you do all of these things. So it lets you basically take enterprise transactional capabilities to your cache. Now I'm going to move on and talk a little bit about a sample application that Alex Snaps, who's also on the line, is going to demonstrate for you. Alex is the author of this wonderful sample application. He built this with the idea of showing off a fairly rich example of how you may use JTA in a real-world scenario. So Alex's idea was a fairly simple one. Is in the dream that if he had a Swiss bank account and he could have money transferred to it from bank accounts all over the world, how would that work? And the idea of this sample app is real-world in that this isn't how the international banking system works. Alex probably doesn't have a Swiss bank account with money flowing into it from all over the world. I bet you wish he does. But the idea here is not that this really models how funds transfer works, but it models the idea of operations taking place, and if the operation with multiple XA resources, and if the operation, any part of the transaction fails, there's a full rollback across all of the XA resources. Just a little bit about the technology of the example, and I'm going to let Alex take over and actually show you the example and talk through how it works and show you the code in detail. So what it is it's a Spring-based Java web app. It's running in a Jetty container. It leverages ActiveMQ as a JMS server. It has two databases, both Derby, XA. It has two caches, a local and a remote cache. Those are Ehcache 2.0, again as XA-enabled JTA-compliant caches. The sample app is using Atomicos Transaction Manager, and that is managing all of the XA resources. The transaction demarcation is done using Spring AOP, so basically just @transactional is used to annotate the classes. So that's the high-level view of the application. What I'm going to do now is hand it over to Alex, the author of the app, and to talk you through, to give you a demonstration and talk you through how it works. So over to you, Alex.
Hello, everyone. So I'm going to indeed show you first the application running so that you get to see what it does, then I'll explain a little bit more how it works. So I'm just going to run this using Maven here. That's going to bootstrap the app, create a bunch of bank accounts that we're going to steal a little bit of money from. I feel like a movie star doing those kind of things. So the application is starting, and we'll be creating those bank accounts and put some money on them. Once that is done, should be able to connect to the web front end of the application. There you go. And here we see how many accounts, how many transfer we got from the ActiveMQ server up here. And then we see how many we managed to execute successfully and how many failed. Every failure is actually fake, so we create random errors. I'll show that later in the code. But so basically every error generates everything to roll back, meaning that all databases that were updated are being put in their former state, as well as the cache. So when we execute a transfer, we actually store how much data, how much money was transferred from that bank account to ours. So if I do a sum in the database here of all the money transferred, I do see $20,000. And if I look in the cache, which is plainly the amount of data that the amount of money that we expect to be on the bank account, we see that these two match. So again, as you can see, there were 50 errors consuming those 2,000 messages that were actually put on the queue. So we execute the method 250 times. So if I now run this very same application, but not being XA, turn XA off, we'll see that you get completely different results. So again, with a little bit of time to populating the bank accounts. And then I'll refresh here. There we go. So that's the initial state, and it starts putting messages. And as you can see very fast, current balance, which is the sum of all the transfers on my bank account in the database, starts drifting from the value that we have in the cache. Because obviously every time we do a rollback, that the update that we did to my balance in the cache wasn't rolled back, and so I should only end up with as many. Should end up with 250 times $100 that we transferred. So now here you see, so there were 200 transactions recorded, every one of $100 US, and you can see that I have way too much money in my bank account. So while this is even better, actually, somehow my bank would realize that, and so the whole evil scheme to become rich would fall apart. So let me switch back to the slides and explain a little bit what you've just seen. Right. So as I said, when the application bootstraps, it creates in the local database, well, what I actually call the remote database, bank accounts with a certain balance. I think I create like 200 different bank accounts with every one $1,000 US on it. And then when that is done, the app starts up and Quartz starts putting messages on the queue every 150 milliseconds saying with data about a transfer of $100 US from one of these bank accounts to my Swiss bank account. And Mike is sadly right, I don't have that one. So then message containers, as you would know from Spring, are sitting there, so like kind of message-driven beans are there and consuming those messages. Every now and then they randomly generate an error. So, but really at the end, so when the local account has been updated and the cache have been updated and everything, and when that error happens, we expect everything to be rolled back. So you could follow how that went through on that web page that was there. Actually, it only runs in a web app so that you can see a human understandable interface to it, but this application shouldn't necessarily be a web application. So exactly how that works. So again, so we have two databases sitting there. One is sort of a persistent cache about data that we would actually get from other systems, which contain a balance for remote bank accounts, right? We have another database that is, let's say, the local one, where we don't simply store balance. We actually store every record that happened to a bank account. So in this case, only transfers, right? So my account is empty. I have no money on it. And then those transfers come in and they are being executed. Obviously, that's the kind of things where you don't want to lose data, so you better have all these things in sync. So with a database and a JMS queue, you would do that easily by setting them up in an XA compliant manner. Though obviously this wouldn't scale so well, because if you would have many transfers coming in, you would all the time be issuing select sum from the transfer table to know the balance of local accounts, and you would like hit the remote database all the time to know what is the amount of money on remote bank accounts. So this is where we put the cache in between, and obviously these cache need to be kept in sync just as much as the database or the queue for that case, because in case something goes wrong, we want to be sure that message is being put back on the queue and doesn't get lost, right? Those bank transfers are worth some money. So now I'm going to show you a little bit how that all works in code. And there isn't actually very much to it, so that is a standard Spring configuration file where we got this account service that does all the magic for us. It needs a reference to a cache manager, Ehcache cache manager. So there isn't much you have to do actually in Spring wiring to have that working properly. In contradiction to database and JMS setup where you need to be sure that a whole bunch of things are set up properly. In this case, you simply want to create your cache manager, providing it with the XML file that you probably know already from Ehcache, but we'll have a look at that in a minute. And the only thing that we're saying is that be sure that Spring only creates this cache manager once the transaction manager has been created. So we know a transaction manager is in the environment, and then Ehcache can pick it up automatically and do what it has to do to register with it, and have the cache behave transactionally. So the rest of the magic happens indeed in this Ehcache exe file, which is this one. And so it's a pretty standard file. It creates those two caches, the account balance cache, which is the local stuff that we'll be storing, and the remote balance cache. As you can see, the only thing we did was specifying exe as a transactional mode and specifying that it has to be a Terracotta clustered cache. The remote balance cache is slightly different. It has a cache writer. I won't say much about this. You'll see a little bit later in code why that is there. That is also a new feature of Ehcache 2.0. Now if I go back to the actual account service implementation, so as Mike mentioned, this is all powered through the add transaction annotation, which basically makes sure that when we enter this method, everything that happens in this method is within an exe transaction. So a little bit of magic here to register the stat synchronization so that we see stuff that's failing and transactions that are failing and transactions that are succeeding. So we get the data from our cache, so that the account data is the balance of every cache. If the account we're executing from is local, we save the transfer. So we actually save, okay, that much money goes into the database. Well, it goes to this bank account, and that we store in the database. And we update the balance in our local cache, and we put back in the cache. The same in case the two account. That is the bit in our case that is being executed, as it all goes to my bank account at Switzerland. So we save the transfer, we update the bank account, and in case it's not a local one, we simply update the balance in the cache. Again, we update the cache. So this is where we actually, based on the data, we go look if it's a local bank account. If it is a local bank account, we simply put it back in the cache. So account code and account data is the amount, the balance of that bank account. And in case it's a remote one, we put it back with a writer. This will actually have whatever we put in the cache be written to a database in the back. Again, since this database is exe as well, it all happens within the same transaction. It's an all or nothing approach. Either everything succeeds and you have all your exe resources in sync, or everything fails and all the states get rolled back. So I think that's mainly it for the application.
Hi, everyone. If you have any questions, please type your questions in the Q&A panel in WebEx, and we'll address those online here, and we'll sort of sort them together. So one question I had just listening to this, Mike and Alex, is if you want to take advantage of this JTA functionality we've seen here today, and you're already using Ehcache, do you have to deploy a Terracotta server array to do that? So I guess I'll pose it to Mike since he's here.
Yep, let me get that one. Thanks, Jeff. So the simple answer to that question is yes. So the more complex answer is if you're using Ehcache today, perhaps you're using it as a standalone cache. So you have a local library, there is no distributed cache, or maybe you have a RMI-based replication where you have several nodes running with the Ehcache caches, and the data is being replicated in a best efforts manner between the caches. If you want to switch to JTA, so if you want a JTA cache, you need to install a JTA, need to install a Terracotta server, which basically provides the infrastructure to enable JTA to work. So enables us to actually deliver the guarantees across the distributed environment for that JTA resource. We are considering adding a feature in a future version of Ehcache to let you use JTA with local cache only. So if that's something you're interested in, then please let us know. One also thing I'd like to note about the Terracotta server array is that actually deploying a Terracotta server array for someone who's working with Ehcache today, either standalone or RMI, is a really simple, straightforward switch. So basically by starting a process, which is just a sort of a Java process, doesn't need to run in any app server or container, it's just a raw JVM process, and you can run multiple processes for HA and for scale out. All you have to do is start that process, even with the default config, that will get you up and running, and then you just change your XML config for Ehcache to say that you're Terracotta clustered rather than local or RMI replicated, and then you're up and running with a distributed cache using the Terracotta infrastructure, which gives you coherence across the nodes and high performance and unlimited scale out. And now with the Ehcache 2.0, gives you the ability to have a JTA compliant cache working as an XA resource.